Yeah.
Okay, so welcome everybody to the DTP colloquium. Today it's a great pleasure to have Manas Kulkarni here from ICTS. Manas did his PhD in Stony Brook, and then he was a postdoc in Princeton, and then he's been faculty at ICTS. So great pleasure to have you here. He's going to tell us about random matrix theory.
Thanks. Yeah. Thanks a lot, and thank you all for coming. It's wonderful to be back in Colaba after a long time. So today I'm going to speak about random matrix theory and open quantum systems. A big part of my talk is going to be about open quantum systems, but I'll also at a later stage talk about closed systems. And also a big part of my talk on random matrix theory will be mostly on non-Hermitian matrices, but I time to time talk about Hermitian matrices. So the talk is centered around non-Hermitian. So when we say non-Hermitian, basically couple of things occur to us. So it's centered around, as I said, non-Hermitian. So three things immediately occur to us. One is open quantum systems. What I mean is that you have a system coupled to a bath. The whole thing is closed. The whole thing is isolated. But if there is a systematic way to integrate out the bath degrees of freedom, can I get an effective non-unitary evolution? Can I get an effective non-Hermitian system? So this is what I would like to call an open quantum system. A system where you start with a big Hamiltonian and you integrate out a huge number of degrees of freedom to get an effective description for some reduced density matrix. The next thing that can occur to us is just non-Hermitian Hamiltonians. So the next thing that can occur to us is you just start with a Hamiltonian which is just non-Hermitian, not bothering about where it came from. So take your Hamiltonians that you're used to and make the frequencies complex and break hermiticity. So that is the next thing that you can think of. You take your harmonic oscillator and make it non-Hermitian by making frequencies complex. So that is one class of non-Hermitian Hamiltonians. And the third thing that can occur to us is just matrices. Can I just study without bothering about where they come from? Just non-Hermitian matrices. So in this talk, I will focus, this is going to be my part A, where I'm going to talk about non-Hermitian Hamiltonians. Hamiltonians, as you will see, which are just non-Hermitian to begin with, without bothering about where they come from. The second part will be open quantum systems. I'll give an example of a system which can be carefully handled such that you can integrate out the bath and get an effective density matrix description and studying properties of those open quantum systems. So I'll not be talking about this, but we have some nice results on just non-Hermitian random matrices. But this is going to be my part A and this is going to be part B. So this is part B. Part A is done with Soumi Ghosh, and who is a postdoc, and Sparsh, who is a student, and part B is done with Mahavir, who is a student at ICTS, and Kamil, who is a colleague, collaborator at ENS Paris, and Hari, who was a postdoc in ICTS and now is in Irvine. And the third part, these parts will be not so long, so we will, I'll try to cover as much as possible. The third part will be isolated quantum system. And I will speak about a particular dimer model where you can see things like localization, chaos, and connections to random matrices. And in this particular model, we are going to speak about self-trapping, localizations, connections to random matrix theory. This particular model has a nice classical limit and some very unusual chaotic and ergodic properties and some quantum classical correspondence and mixed phase space and so on. So this is the plan, but I think this is time limited, right? So I have an hour or something. Is that
roughly an hour?
Roughly an hour. Okay, thanks. Okay. So this is the plan, and so before proceeding further, let us just recap some possible quantities that can be extracted from real and complex numbers. So basically, I'm going to set the stage because many of these things will be centered around eigenvalues and how to deal with eigenvalues of Hamiltonians or matrices and so on. So, but before that, if I give you a set of real numbers or complex numbers, what are the possible quantities that you can extract? So let us say that if you have real numbers, let's say we have n real numbers. Let's not worry where these numbers came from, E1 to En. Of course, the zeroth order thing, the simplest thing is to just ask what are the density of these numbers. So that's the first thing one would ask, what is the density of these numbers? You can think of these as particles and you can say positions of particles, and first thing that can occur to you is what is the density of the positions. So that is sort of there already, but as you will see often, density of numbers is not very useful beyond a point. So that's why I sort of highlighted three things here. The first thing is level spacing statistics. So this is the spacing distribution. So spacings between all these numbers, and there are statistics of that distribution. So you have 100 numbers, that means you have 99 gaps, and you make a histogram of that. That is called level spacing statistics. That's the first quantity. I'll keep reminding about these quantities. Next is the adjacent gap ratio. This is basically the minimum of adjacent gaps by the maximum of adjacent gaps. So you can again see how it comes about. You can start with 100 numbers and you can see what this quantity is. It's just minimum by maximum of adjacent gaps.
So this is a single number, or not?
This I is minimum of, let's say, a 7th and 8th gap by maximum of 7th and 8th gap. And then you make histogram of those.
Oh, min max over the random answer.
Over the random answer. Exactly. Okay. The third one is spectral form factor. So this is
min max is that between these two numbers, which is bigger and which is
smaller. Yeah. Okay. So this is the spectral form factor. So this is a quantity where you see that many of these things were focused on adjacent things or nearest neighbor things. This quantity is the spectral form factor, of course, very well studied and well known. It gives you some sense of correlations between far eigenvalues. And this is the quantity which we are going to discuss later, but it's just e to the I tau em minus en sum over all m and n. Okay, so this is spectral form factor, this is some connected SFF, but these are just quantities that we should look at. Now, if these numbers are complex, then how do we sort of define analog of these? So that is not too difficult. Level spacing statistics, you can again think of some numbers on the complex plane, and basically if there are 100 numbers on the complex plane, every number has a nearest number, and you make statistics of that. So you can easily generalize this to the complex plane. This is minimum distance of an eigenvalue on the complex plane. That's clear, right? So
no, it could also be complex, imaginary. Does that work? Like if I have 2 points which are at the same value of the real part, but different values of the imaginary part, then that is also level spacing?
Yeah, sure. So imagine that you have this is a complex plane.
Right.
Imagine you have some 7th eigenvalue is here,
Right.
and say 8th is here, and then 9th is here. And let's say these are the same real part, but slightly different imaginary part. Then this distance is the distance corresponding to the 7th eigenvalue. You just have to.
That qualifies as a level spacing.
Right. That absolutely qualifies. Yeah. So you just look at you take a point, see the nearest point around it. What is the distance? Then note down that number. Go to another point, see the nearest point, note down that number. And these are all you'll get a number of distances, list of distances, and then you make a.
Yeah, I got the concept. I just realized that even purely complex imaginary distances qualify level spacing.
Yes. Yeah.
But you can have multiple points in principle which are the same distance.
Yeah.
Like the real axis.
Right.
Is not, there's no unique ordering, right? So
Right. But if you take a number like a number here. I mean, the chance of having bunch of eigenvalues with exactly same distance, same minimum distance, I mean, that is very unlikely. But if that happens, sorry?
Is it a set of measures zero?
It's a set of measures zero, especially when you're looking into non-Hermitian random matrices. So I'll come to that. You'll literally see the distribution. I'll show the distribution of these things. That's a set of measures zero. Yeah.
The complexity is also you do unfolding.
Here, yes. So there is so I don't want to get into that, but you have to do some unfolding to get rid of the effect of global density of states effect. But that's basic features will remain same. Yeah.
In one sense, these are better quantities to look at for the statistics.
Oh, not only better. I'll show you that if you just look at the density of states, it may not be enough at all. Like two things can have same density of states, but one may be highly correlated, another can be completely uncorrelated. So looking at density of states is not at all sufficient. So these are almost necessary to look at. So I'll show you examples. I'll show you exactly the plots where two things look exactly the same if you see it, but if you calculate these, they're entirely different. So okay, so complex spacing ratio. So here you see this is one eigenvalue. I'm making it numerator by denominator. Numerator is nearest neighbor minus the number, and denominator is next nearest neighbor minus the number. Okay, both numerator and denominator are complex here. These are complex distances. So I guess so. So literally, you take the difference between these two complex numbers, and divide it by difference between these two complex numbers. So first you search who is nearest neighbor and who is next nearest neighbor. Take the ratio. It will be complex number divided by a complex number, and then that can be written as r e to the I theta. So it could be written as r e to the I theta. Of course, indexed by k, and then you analyze that data.
Why is there not? I mean, you have a level spacing.
Yeah.
What happens if you take the ratio of that level spacing, take the ratio of the modes rather than this complex?
Yes. So actually, you can do that, but the point is, some results are known about this in random matrix series. So we use this as a diagnostic. There are multiple ways to make diagnostics. So this is an important point, that this doesn't really map to the old definition. If you put all the eigenvalues on the real line, you will see that this will not map to that. But these are just analogs. They don't need to map it to.
You still get science.
Exactly. Okay, so this is an complexified version of spectral form factor. So basically, this is the answer. So, but let me try to write down how it looks. This is mn going from 1 to n, e to the I. Let me write it in a slightly more explicit manner. So you can write it as t xm minus xn plus ym minus yn s. Okay, so some generalization. Before we did not have this at all. Okay, and I think before I called it tau, but now you have to just generalize it to t and s. So xm, xn are real parts of the eigenvalues. You take that and use your usual spectral form factor. These are the imaginary part, and parameters by an s. Okay, so it just turns out that so this concept for complexified spectral form factor is actually quite a new concept, but it is very useful in getting the analog of this ramp, random matrix theory ramp that we usually see, but for non-Hermitian systems, what happens to this ramp? So for that, it's very interesting. So, okay, so is that?
I mean, in general, people do use it in all sorts of Wigner functions, these complex transforms.
Right.
That's the standard thing people use.
Right.
They write it as functions of complex.
Yes. Yeah. So one thing is that in the context of non-Hermitian Hamiltonians, this is fairly new, very new. And but of course here also you could have made multiple ways of doing the same thing. You could have come up with many other protocols. So, but these are just diagnostics about which we understand things come from a random matrix theory point of view. So our goal is to finally connect this to open quantum systems and non-Hermitian Hamiltonian. So better to start with something we know a little bit about. So okay, so these are so now the question is, what is a good way to produce correlated numbers? So if I spoke about complex numbers, and before this I spoke about real numbers, but what is a good way to produce numbers which are correlated? A good way to produce the numbers which are correlated is random matrix theory, right? Because what you do is you prepare random matrices where random matrix elements are uncorrelated. So you order n square numbers go into the random matrix, but only n eigenvalues come out. So from n square numbers, order n square, you get n eigenvalues. So they are typically very correlated. So that is, so if I can do it with random matrix theory, then I can create correlated numbers. So okay. So I'll not go into too many details of this, but just this sentence is enough. If you have a real symmetric n cross n matrix and the diagonal and upper triangular elements are independently chosen from some Gaussian distributions, then that's typically called a GUE random matrix. And same things for GUE, you have some other slightly different forms. But the idea is take elements of a random matrix, you draw it from a Gaussian distribution. There are some constraints, but I'll not get into that. But once you draw it from a Gaussian distribution, diagonalize those random matrices, and you get a list of real numbers, because these are Hermitian random matrices. Okay, these are Hermitian. You'll get a list of real numbers. Take those list of real numbers and calculate things that I showed you in the previous the slide on real number. So that is about this. So what happens, right? If I do that, I just prepare this real symmetric n cross n matrix. Again, you can focus only on the first row. I just showed the second for completeness. So now the first question you will ask is, what are the density of eigenvalues? So the density of eigenvalues for these matrices are typically a semicircle. Okay, these are semicircle of the form rho of x is equal to, in some scaled variables or even unscaled, in some scaled variables it will be like 2 minus x squared. Unscaled visualization. So it's a semicircle of radius root n. Okay, that's the density of eigenvalues. So they will form a nice semicircle. But I didn't show that. I'll go directly to level spacing distribution. So this is how the level spacing distribution looks. So it goes like this. We know the forms of this. You know the forms of these. In some approximated versions, you know the forms of rho of s. You know forms of rho of r. Remember, r was the adjacent gap ratio. And this is the well-known ramp. This is the spectral form factor, and this is the ramp of random matrix theory. So this is it turns out it's a linear ramp here. Okay, so these are the key features of Hermitian random matrix theory. Yes. So under some approximations, all these are known analytically. Okay, so that is what happens with this, and also exactly how what is the smallest behavior is known perfectly, and everything. So there are many things that are known here. So that is about Hermitian random matrix. When it comes to non-Hermitian random matrix theory, it's even more. In some sense, you just have to again draw elements from a Gaussian distribution, but you don't have to care about hermiticity at all. Okay, you don't have to care about hermiticity at all. You just draw elements from a Gaussian distribution, and then calculate its eigenvalues. The eigenvalues will fall in the complex plane, and the shape they take. So I'll erase this, and the shape they take, typical. These are called juniper ensembles, and the shape they take are what will happen is that the eigenvalues form a uniform disk of radius root n. Okay, this is called a Junipert disk. So for some reason, the eigenvalues don't really form a cap. I mean, in 1D it formed a circle. In 2D it doesn't form a dome. It just forms a disk. But again, these disks are fairly, I mean, okay, you can easily make disks with uncorrelated complex numbers also, right? If you draw, if you use uncorrelated complex numbers and somehow put it on a disk, they will also form a uniform disk by construction. But just looking at the disk doesn't really say much. That's what I wanted to say.
So this is a precise disk.
Precise disk of radius root n. Yeah.
Why is it that the eigenvalues cannot have magnitude more than?
This disk is in the larger limit. In the larger limit, it's a disk. There are some corrections, but in the larger limit, there is a disk.
You could have few eigenvalues lying outside.
Yes. There are some corrections, but in the larger limit, it forms a perfect disk. Yeah.
And the uniform disk.
Uniform disk. Uniform.
Wait, so rho is 1 inside and 0 outside, that kind of is flat, it's not a rho.
No, it's completely flat.
I see.
Yeah.
So there's a jump as discontinuity at the edge.
Yes. So it's like this, and it actually is
Like a fermion.
like a fermion, with some corrections, but yeah.
Corrections are order 1 over root n?
That I don't.
Okay.
I mean, yeah. So precise forms,
There's a fermion-like behavior.
It's a fermion. Now that you brought it up, it maps to rotating fermions.
Yeah.
But let's not. Yeah. But this forms a perfect disk. Also, one more thing is this maps to a log gas in 2D, and it's related to the log gas in 2D. It be eigenvalues of
You
this.
mean that Landau fermions
Exactly.
in a trap.
Those fermions eigenvalues behave like those fermions. But
What is the symmetry of the? Is this symmetric under unitary rotations of these?
no, not necessary at all. Yeah. So within
the ensemble has no symmetry.
no symmetry. So within the non-Hermitian classes, there are ensembles which have some specific symmetries. Like there's something called transposition ensembles. It turns out that they also have very universal features. But yeah, this has no symmetries. Okay, so here is the answer. So this is our disk. Okay, but then the S. So recall that this was my level spacing statistic.
So can one write like matrix model down with some SLNC R measure?
So
Invariant numbers.
I mean, what you can do is you can certainly write it as, just like you write Hermitian matrix models as e to the trace h square. Here it's like e to the trace h dagger, and it goes through.
And they are also quite similar.
Yeah. So
That's the example with symmetry where you have this.
Sorry.
That's an example of where there is symmetry,
Yeah. I'll come. Yeah, exactly.
not just transposition, but the full unitary.
Yeah. Actually, so maybe I think I have. For example, okay. So just so. Okay, so the key features here is that this goes as S cube. Okay, I should have written here. This goes as S cube here, and in the real case, in the GOE case, it goes as S. Okay, but that's just a comment. Here it goes as S cube. This is the scatter plot of this quantity, and you see there is a nice feature here, which is not there in the eigenvalues. Eigenvalues just formed a disk, right? But this has this nice feature, and this spectral form factor here actually also has a ramp, but this is not a linear ramp. It has some form, but this is basically the analog of this is the ramp of the dissipative spectral form factor.
So in GUE, it's also SQ? Usually.
Yeah, so interestingly, in case of non-Hermitian matrices, it turns out that it's S cube even in GUE. And also it is S cube in this transposition symmetry class. So that is not obvious why, but yeah, so
Gin UE and OE.
No, so the GIN OE are basically when you basically make Genoi is where entries of the matrix are real.
Okay.
Okay, but the matrix is of course non-Hermitian. Okay, and in Genoi that is also not stated. Yeah, and in Genoi and Genoi, you have this SQ.
The average value of ZK,
Yes, they're all known.
that doesn't match with GUE.
Not with GUE, but with So the average values of these different there may be slight differences. Yeah. I think the smallest behavior is SQ. Yeah. Okay, so this is clear, right? So now the point is. Just to recap, what happens with uncorrelated numbers? I have been talking about eigenvalues coming out of random matrices, which are clearly highly correlated because SQ here means that they really don't want to be together. And in the real eigenvalue case, it was S, which means they also don't want to. So this is eigenvalue repulsion. The eigenvalues basically repel in random matrix theories. Okay. So if you have uncorrelated real numbers, the gap distribution is basically Poisson. This is level attraction, right? So this is e to the minus s. So you take from some window, you draw uncorrelated random numbers, prepare their gaps, and calculate this. You will see that the random numbers can come close to each other. They are not restricted by. They are not coming from eigenvalues of random matrices. So it is a clear difference between how correlated and uncorrelated numbers should look. Okay. In the non-Hermitian case also, as I was saying, these are all the different symmetry classes. AI dagger is transposition symmetry. A is equal to A transpose, but still it's non-Hermitian. Okay. And these are all going as S cube, and the uncorrelated number on the complex plane goes as S. Okay.
So why is this not like that?
No, because it's 2D, no? So it's because phase space factor. Because 2D even uncorrelated numbers will have this. Yeah. So Okay, so but S and S cube there is a clear difference. So now what happens with actual physical systems, and whether anything comes out of physical in open quantum systems is what I will try to.
Is there a simple argument for the S cube? Something easy to say?
Not simple, but so even if you take 2 by 2 non-Hermitian random matrix, you can work it out. In Hermitian random matrix, you can actually work it out.
Yeah.
Here also you can work it out. Yeah. Okay. So now let's think about quantum Hamiltonians and so on. But before that, I'll just.
Hermitian is S square.
Hermitian GOE is S e to the minus S square. This is GOE. GUE is S square. Okay, with some coefficients here. Okay, so there are a couple of conjectures here, which at some point I will come back to if I have time. But the three conjectures are basically a Berry-Table conjecture, which says that if typical quantum Hamiltonians have an integrable classical limit, then their level spacings are distributed according to Poisson distribution. So that's the conjecture. If there's a classical model which is integrable, the analogous quantum model's eigenvalues have a level spacing distribution that is like a Poisson. I'm just stating these conjectures, maybe because they may be useful later. BGS conjecture is saying that if you have a classical model which is chaotic, okay. For example, if you do this classical billiard problem, this many of you may know, the classical billiard model with curved edges. That classical model is chaotic. If there is such classical model, then its quantized version will have level spacings which are distributed according to random matrix theory. So this is BGS conjecture. Then there's a GHS conjecture, which says that it's the non-Hermitian analog of above conjectures in some sense. It says that those Liouvilleans, basically let's say those non-Hermitian, those systems which have classical dynamics that are integrable, then their complex level spacings are distributed according to two-dimensional Poisson. But if classical limits are chaotic, then they will map to non-Hermitian random matrix theories. Yes, so it's a non-Hermitian version of Berry, Tabor, and BGS. So again, these are just conjectures, basically studying chaotic and regular aspects of classical and quantum models are exciting, and eigenvalue analysis will hopefully say a lot. That was the reason I wanted to, present these conjectures. But it's very hard to test these conjectures, and there's not many options. And this is why the part 3 of my talk shows that this model, that model has a potential nice platform to test, because you first of all need a classical limit. So if you work with spin chains or XXZ spin chains and all, you don't really know how to take classical limit. So you need a classical limit, and then it needs to be doable. And many of these things are few body, but then many body examples are even less. So yeah.
So when they say, then there is some assumption that this is, when you say sort of integrable limit, there is some sort of a random integrable limit, that it's not some very symmetry specified. Like, would it work if the integrable limit is just a free particle?
Okay. So there are some. That's why I had this word pathological cases. So in there's some cases which are highly pathological. For example, quantum harmonic oscillator. Right? What is the level spacing of a quantum harmonic oscillator? So there are these cases, but so this is generic. Yeah.
So the stuff that comes out of Bethe answers, etc., is well known to have some level space.
Yes. So if they're Bethe integrable systems, you can see that the level spacing statistics are Poisson. But then the point is, these conjectures are more quantum classical correspondence. So, but yeah. Okay. So I am doing. Is that working, or is it going faster? Or no. So part A. This is part A. But anyway, I think I can go fairly fast. But what I wanted to say is that part A was where I said that the Hamiltonian itself is non-Hermitian. Okay. So I have model 1, model 2, and model 3. But all I'm doing is, these are typical models that you would have seen. These are models of hardcore bosons. But I just make it non-Hermitian by having e to the g and e to the minus g. Okay, if g is purely imaginary, it's Hermitian. But if g is 1 or something, then it's so this is what I call hopping non-Hermiticity. And model 2 is called on-site non-Hermiticity. So what I do is, I have some on-site term, some hi, ni, and I will just make this complex. Okay, I think it's better to use hj and nj. So hj, I can call it I shift it to minus 1 power j something else. Okay, I've written the form here. So this is plus I gamma, minus I gamma, plus I gamma. The third is basically like second, but it's a long-range model with hopping non-Hermiticity. Okay, is that so? This is basically the schematic description. So this, I wanted to say that some of these effective non-Hermitian Hamiltonians you can actually argue with some approximations coming from open quantum systems, but let's not get into it. There are some ways of making sense out of this, but there's a huge community of people who just study these kind of non-Hermitian Hamiltonians, and here H is basically disordered. So that is what is going to give you your samples. In random matrix theory, we can easily make our samples, but here disorder is coming through H. Okay, so that is a now if I have this hopping non-Hermiticity.
Sorry, what do you mean? This is what we make samples. Now we make samples.
Right. So this hi basically you draw it from some random number between say -1 to 1. So you make your first Hamiltonian. You have like 1000 Hamiltonians, and that's it. So okay. So that is a thing.
So you use a flat distribution -1 to 1.
Yeah. You typically use a flat distribution of -1 to 1, but it doesn't matter most of the time. You can and many times you don't even need to make samples, because if you have a large enough Hamiltonian, you can calculate level spacing statistics and all. So it also depends what you want to calculate. So for clean integrable models, you can get Poisson distribution, but there is no sample there. It's just so. Okay, so I'll tell you some interesting things that happen. So in model 1, for example, H is my disorder strength. So think of H as disorder strength. And for low disorder strength, eigenvalues are all over the place. They are complex. So this is so the way this is done is typically these models are exactly diagonalized at half filling. Okay, so you have typically you can study L equal to 18 sites at half filling, and you can exactly diagonalize the problem. You can work in a particular half filling sector, and you can exactly diagonalize the problem. So when I make the disorder high, it turns out that all the eigenvalues collapse on the real line. So this is just property of this model. Okay, this is just property. So this model undergoes a complex real spectral transition. So here we are talking about spectral transitions, like transitions in the properties of the eigenvalue spectrum. So this is what happens.
So what is that? Why is that? Is there a semicircle also?
No. So this is So this is what I wanted to say, that typically you don't get these semicircles and disks, as I will show you. But what you will get is the other properties. In fact, this is also, for example, this is not a nice disk, right? So you don't get the semicircle. But when something becomes from complex to real, what you typically do is you assume they are real numbers and do the analysis as if they are real numbers.
But is there a transition? I mean, if I just make H very large, then it's dominated by H, which are real. So I would expect the eigenvalues to be real, and the small non-hermiticity will push it a little bit into the complex. Right. But there's not formal transition.
So at this moment, the status is that there's the same level of transition as in the traditional Hermitian many-body localization community. So there's the same status. So if you do, there's some finite size scaling you can do, but it's exactly so. Basically, to the sizes we have, it looks like a transition, but one can never be 100% sure. Yeah. In fact, I have some plot actually. I'll show you next. I'll show you. Here I just wanted to show you the eigenvalue clouds. Okay. So in the model 2, the eigenvalue cloud here is some cloud here, complex cloud, and when I make the disorder high, it's again a cloud. So nothing special is happening if you just see the eigenvalues. They're changing the shape a bit, but doesn't mean anything. But the level spacing statistics are drastically different. One is Poisson. This is Poisson, 2D Poisson, and this is Geneva. So you drastically see the
What in the previous case in the strong noise limit?
In the strong noise limit, what happens is that this becomes 1D Poisson. Yeah.
So if there is no disorder, what happens? If you get Poisson?
Oh, if there's no disorder here?
Yeah.
If there's no disorder, I would say that it's still a non-integrable model. So I would expect you to still get random matrix theory. So I think you are using disorder to sort of see transitions here. Yeah.
What's the effect of tuning gamma?
So that presumably it's going to change the transition point a bit, but I don't think there'll be any drastic effect. Yeah.
So what is used as a diagnostic for the transition? Like, is there a quantity which, because right now I'm just saying to.
No. There is
a quantity?
There are quantities.
Track the.
There are quantities. Just single number quantities that track.
And the other question was, one of the reasons this R was introduced rather than the level spacing was, if you just do the level spacing, there is actually in a real Hamiltonian, anybody Hamiltonian, there's actually a lot of energy dependence to that statistic.
Absolutely.
Whereas R remains relatively energy dependent.
Exactly. So
is there something similar that is seen here?
Exactly. So here also we are going to use R actually, our R, the complex. And in fact, average of that R is the if you want to say order parameter. Yeah, these are just visual pictures. Of course, it's not, but I mean, it's clearly this is clearly in the random matrix and it's in the Poisson, but we need some, especially when we are changing disorder strength. But so this is model 3. I'll just maybe I'll skip model 3 altogether. It's just some long range model where alpha going to infinity corresponds to nearest neighbor and all. But there's no time, so I'll just skip model 3. Okay, so this is how all these disks look, and 2D Poisson also looks like a disk. I mean, I showed it on a square, but if you make a disk, it will just look. So they all look the same. These are 3 random matrices, all look like disks, and this is also Poisson, so there's no difference. So the finite structure contains the information. So now let us just see what the finite structure will contain. So this is again showing you the same plots. Just model 1 and model 2. I'm showing the same plots. Let's skip this. Yeah. So this is just recap. Okay. So this is a recap of random matrix theory and uncorrelated complex numbers. So this is the distribution of R, and this is the distribution of theta. Remember the R e to the I theta was some Z, and Z was ratio of the numerator by denominator, which was complex by. So you see that there are slight differences between different random matrices. These are 3 very common random matrices, non-Hermitian random matrices, and 2D Poisson is just a straight line like this. And here 2D Poisson is just flat here. So there's a big difference between Poisson and random matrices here. And the distribution of this distribution basically had this interesting structure in random matrix theory. And for uncorrelated numbers, even this doesn't have any structure. Okay? So you see, the densities, all of them were disks. But if I plot this, then only this remains a disk. And these remain, they have some hollow parts here. And if you think about it, these hollow parts actually have meanings. It's like saying that 3 eigenvalues cannot, the probability that they'll be on a line is less and all, but let's not get into that. But if you think about it a little bit, why there is this thing here, you can sort of argue what happens. Okay, so this is just this thing, and so this is exactly what we calculate for model 1. And if you do it for model 1, then you basically have exactly this this distribution for R. So this comes back to Rajdip's question that this is okay. I don't want to get into that, but this R is sort of, it gets rid of some non-universal features. Let me put it this way. So R, and whatever you do with R, you can be slightly more confident. And you see that there is very good relation between random matrix theory and that model 1 Hamiltonian that I presented. I also have numbers for expectation value of R and all. They match the expected numbers from random matrix theories. Oh, sorry.
R is the modulus of ZK.
Yes. R is the modulus of ZK, where Z is R e to the I theta.
But the average value of Z itself doesn't.
Yeah, that is like R cos theta average value. So that we did not calculate. Yeah. So we typically calculate average value of R and average value of cos theta. These are there. That's the same. So this is similar in model 2. In model 2 also.
Sorry, this is probably a little. So you are comparing your models to basically 2 classes. One is uncorrelated, the other is Gaussian. That's right.
Non-Hermitian Gaussian. Yeah.
So this is probably a very broad question, but in general, is there no other class that one can compare this to? Is there some universality that a given model must look either like this or like that in some limit?
So it turns out that if usually what happens in these cases is, suppose it looks like in between those two, or let's say closer to one, but not really that. Usually people say that it's a finite size effect. If I do larger and larger system size, it will tend to random matrix. No, there is no very rigorous reason, but there are examples where it is neither. But there is no very.
For example, if you take correlated matrix entries to be correlated random variable rather than uncorrelated. Yeah, the correlation is coming when you are getting the eigenvalues.
Okay.
Suppose you already start with a correlated matrix, then you can get
Get different power laws.
depending on how long-tailed your distribution are and stuff like that.
Also, I'll show you in part. Okay,
That is
part,
for real. I don't know for complex.
right. Also, if there is no large L possibility, if the system is such that there's no nice parameter to take thermodynamic limit, then you may get stuck in middle and it may go to this thing. That's what is happening to part C, but I don't know whether. So this is model 2, and then let's skip model 3 altogether. So yeah.
So when you see that complex to real transition, does this show up in your R here? You are showing this complex to real.
So the complex to real is a little bit complicated because when we are on the real side, we use the real definitions. So there's a very one subtle thing which we are suffering with because how to smoothly take the limit is unclear.
This doesn't go into that.
Exactly. But in model 2, this problem is not there. And there, I think, if you calculate this R as a function of H, there is some, I forgot how it looks in non-Hermitian case, there's something like this, which if you do system size scaling seems to, be similar to all the many body localization literature. So that is yeah. Okay, so I'll skip model 3, but I just wanted to say that these spectral form factors also, so this is what I think somebody was saying. So these are some exact expressions are known for the random matrix theory, non-Hermitian random matrix theory, and for Poisson ensembles in complex numbers, and so these is how they would look if you plot them and so on, and basically I just wanted to show that you actually get a nice ramp for weak disorder, and when you increase the disorder, this ramp just goes away and it becomes like this. And this is how it will look for 2D Poisson numbers. Okay, so and there are different details, but basically you can see this non-Hermitian ramp analog in these models. Okay, so now what about setups where non-Hermitian Hamiltonians are not phenomenological? So although these kind of non-Hermitian Hamiltonians are extensively studied, there's a big community which studies this, and you can really argue that they are physically can be quite relevant. Even though it may look like you have ad hocly made something non-Hermitian, there's some arguments. But now what about open quantum systems where there is where it's not phenomenological? So one example, I have 15 minutes or 15 minutes. Okay, so then So let me just this is a large spin system. It's called the decay model. It's basically a bosonic mode coupled to a large spin in this fashion. Okay, so I'll not go into details of this because part C has a large spin system. So I'll just quickly say that you can, if you couple this bosonic mode to a path of a harmonic path and integrate out the harmonic path under some approximations like Born-Markov approximation and so on, you'll get some Lindbladian form. So you will have this Hamiltonian and have this Lindbladian. So you'll get an effective equation for density matrices of your system. And this density matrix has trace preserving property and all those properties. So it's a consistent theory. It has its own issues, but it is a consistent theory. It has its limitations in the sense of approximations, but you can study the eigenvalues associated with those problems. So let me just write formally what will happen is that you have something like this plus some, let's say some non-unitary part. Okay, this is a unitary part. You can sort of write this density matrix in a vectorized form. If it's like n by n density matrix, you can write this n cross 1. It's just useful to write it that way, and then you can write it like this, where this will be like n square cross n square, and you can study eigenvalue properties of this, and it turns out that those also have connections with non-Hermitian random matrix theories and 2D Poisson. So that is the
The spin was the path. Okay.
No, here this is the system. The path is something else now. Yeah. Here the system contains this harmonic mode and the large spin.
No, and your Lindbladian, I didn't see the spin.
Oh, exactly. So here only the bosonic mode is coupled to a bar. The spin is not coupled to a bar. So what happens is that if you have a spin also that's coupled to a bar, then you'll have a Lindbladian for spin. It becomes a slightly more complicated problem, but mostly you will see similar this thing. Okay, so this is here the story is different. Here it's not a disorder problem. It turns out that for weak coupling, there's actually a dissipative quantum phase transition. But here we see that when you change the coupling from weak to strong, you actually go from random matrix theory to Poisson. Okay, so this is a slightly different story, but a story where somehow there is a spectral phase transitions happening around the same time, where there is also a dissipative quantum phase transition. Although these do not have to be together at all. This is the point I want to just say, that this is just some transition in the spectral statistics.
Manas, I have some questions similar to what she has asked. So you're coupling these oscillators to an external path.
Yeah.
So you're taking a partial trace over the path as well as over the spin.
No. Partial trace only over the path. So my rho dot here, rho dot, which was what I wrote here, this has the bosonic mode plus this large spin.
Right.
So this density matrix still has both.
Okay, but the dissipation part has only
the dissipation part, which is typically written like this,
involves only the oscillator.
Involves only the oscillator. So if you want to write a microscopic theory, you should add one more Hamiltonian system resolver, which will be like this: A dagger BK plus Hermitian conjugate. Let me call it GK, and then the reservoir itself is omega K BK delta BK. That's it. Typically, if you want to also couple the spin, then typically you can add this kind of terms.
Okay. So the spin is there to break the integrability in that.
So in this case, actually, the spin breaks the integrability.
Spin breaks the
integrability. Spin breaks the integrability.
Without the spin, you would have an integrability.
Yeah. But there's one more. Okay, I'll come to part C. There's one story, but yeah. So there's this. Okay, but anyway. So here these are just complex spectrum of the Lewisian, and actually I just wanted to mention that here. In general, this is an interesting quantity, this L matrix, because if there is a unique steady state, then there better be a eigenvalue sitting at 0. The eigenvector corresponding to the 0th eigenvalue is the steady state. I mean, in general, I'm not talking about this problem, but in general, not only the spectrum of this L, but also the lowest eigenvalue, the existence of a 0th eigenvalue, the next eigenvalue determines the rate at which it goes there, and so on. But
so one question which I had is, your real, once you go to the real valued, close to the real valued thing, you would also get probably an S out of simply being a real valued random matrix.
Which is?
So I'm saying the fact that you are getting S to SQ, right?
Yeah.
If you had almost all real eigenvalues,
yes,
which was what was happening, would you also get an S?
Yes.
So how do you distinguish between?
Okay, so there is one thing about this, which is an earlier story. Suppose I did not have this at all, this Lindbladian, this piece. Okay, then you could do the Hamiltonian. You could study Hamiltonian. There also there is actually a Hermitian random matrix to Poisson. So if you slowly remove this thing and make the eigenvalues real, finally some effective eigenvalues should get the S. But again, it's the same problem that even there is the same problem that if you have real numbers, the level spacing statistics and my
definition is
not reaching. So actually, to make my definition to reach, there is something called closest neighbor. There is some definition which actually goes there, and closest neighbor for Hermitian random matrices, there are also results. So we are thinking about that. So yeah, it's a bit going from open to close is a little non-trivial. So okay, so I'll skip this. So these were some numbers.
Manas.
Hi.
Since you, hi, this is Kedar on Zoom. Since you mentioned the zero eigenvalue and the Leuvenhoek, maybe this is the right time to ask some question I had from the beginning. You gave
Sure.
these different classifications of
Yeah.
what kind of non-Hermitian matrices arise. So I was just wondering, there's a class that statistical physics cares about a lot, which is you just write down the master equation for some interacting particle model, classical. And there's a stochastic matrix, which is the master equation right-hand side. It has row sum 1 or column sum 1 or something, right? It's a rate equation. So presumably the Liouvillean you're talking about is one example of something like that in the context of Hamiltonian dynamics, right? I mean, you can take any interacting particle model of the type Pradeep likes. It has a master equation.
Right.
There is a right-hand side, which is usually a non-Hermitian matrix.
Right.
It's a stochastic matrix.
Right.
So now one can look at, so that at least for me is a very naturally occurring class of non-Hermitian matrices. And I'm wondering if that fits into your classification somewhere.
I mean, it could very well be that what you're talking also might go to Gin-Hui non-Hermitian random matrix. It may go to the random matrix theory which has no symmetry at all whatsoever.
Okay.
I think so. Yeah. Because so
I think Kedar, what you're talking about are rates, which would
That's
be
correct.
squares of, if I roughly think of things, squares of matrix elements with some extra pieces.
Yeah, what I'm talking about is what people call stochastic matrix.
I
The right-hand
think
side
if
of a
you
master
want to
equation.
compare from here, using some Fermi-Golden rule type stuff, it will not be the matrix elements, but some
So
sort of...
I know, but I'm just saying in his original classification of different kinds of situations in which random matrices which are non-Hermitian arise, this is a very natural class of non-Hermitian matrices whose spectrum we care about, right?
Yeah.
So I was just wondering about that.
In those stochastic matrices may not be random. If you take a
But if the rates are random, if I'm looking at an interacting particle system where the rates are position dependent,
right?
Okay. Like an interacting diffusion in a random environment which people have studied, then wouldn't it be a very natural kind of random non-Hermitian matrix?
No, but their sums have to sum up to something, so they are correlated random. The matrix entries themselves are
but the number of correlations is very small. It's the number of rows.
Because of some
order rather than n square.
Yeah, I guess if the number of correlations are measure zero, in the larger limit eventually it should again. But it's not clear. I'll think about it. Yeah.
Okay, thank you.
Yeah, sure. Okay, so by the way, these were the numbers that Rajdeep was asking, that you have some standard numbers for GUE, Poisson.
So when you said that this transition coincided with the dissipative quantum phase transition, that's by looking at R, expectation of R and how it transitions.
Correct, absolutely. And we know where the quantum phase transition happens.
Yeah.
Okay, so I'll just spend 5 minutes.
Yeah, you can go on for a bit more.
10 minutes.
Several questions.
Okay. So let me just switch gears to part C, which is again talking about large spin model. So I didn't spend much time there, but so basically this is what I would call a dimer model of a specific type. So this has two units, the left unit and right unit, and each unit is my harmonic oscillator with a large spin, but the coupling is of this form. Just A dagger S minus and AS plus. It is slightly different from the other coupling. So this is why because of this coupling and because of the symmetry, total excitation is conserved here. Okay, and then this is called a dimer because I can hop. I'm going to hop the bosonic modes here. So this is my this is called Tavis-Cummings model. This model alone is integrable actually. The model itself, the unit is integrable, but the dimer is not. So you have this Tavis-Cummings model, and it is coupled to this thing. Okay, so this is just and you can think of this as collection of n two-level systems as single n+1 level system of large spin. Okay, so there are some details here, but I will skip it. But this is the model, and this is the model. nothing, no bath, completely Hermitian problem. It's just an isolated quantum system. Okay, so now we are asking slightly different questions here. So let me think of this as 2 units, and we are asking this question about imbalance. So what is imbalance, right? So these are 2 units with some large spin. This is the coupling chain. Okay. So suppose I create some initial condition where I start with some 50 bosons here, okay, and let it evolve according to full quantum dynamics. What is going to happen? That's the question. The question is whether it will go back and forth or whether it will get stuck here. So this is very different than my first part of my talk. And it turns out that if lambda is small, notice that lambda is this one. So J is the hopping. Lambda is the very important parameter. Lambda is the interaction term between my last spin and my bosonic mode. If my lambda is small, then my imbalance actually goes to 0. Okay? And if my lambda is large, my imbalance remains whatever. I started with 50 bosons, it just gets stuck there. Okay? So there is a self-trapping delocalization. And here also we believe it is some sort of transition, but I'll come to that. Okay? So this is what. So imbalance basically goes to 0 when the interaction is weak, and imbalance is finite when the interaction is strong.
So the interaction would have intuitively been volume.
No, because if you have some interaction here, if you have strong interactions, this is exactly. So J is hopping. Okay, so J you can forget actually. You can put J equal to 1 for all purposes here. But if I increase the interaction, I tend to trap this. So this is one this thing. And here we can compute something called like this is like some total imbalance. Total number of excitations here minus total number of excitations here, divided by total number of excitations. But that is total number of excitations is conserved. Okay, but we compute the total number of excitations here minus the total number of excitations here. And so when interactions is weak, it will try to slosh back and forth, and then it will just is all over the place. So this is just exact quantum dynamics calculations. Okay.
So what is the time scale I should be actually looking at? So microscopically, once I have a large, now there's a time scale which is no longer governed by J. I would
right.
Maybe some square root n or something that will come into that picture because you are strongly tied to the spin.
Right. So I'll maybe answer your question in the sense that one natural thing in this business is to understand how steady state imbalance scales with things. So that still doesn't answer your question, I guess. But
I was just wondering if you go to larger, whether it will fall at some point when it becomes order n. In terms of.
So no, I think certainly not. So here there are 2 things. First of all, one is S, the large spin. Okay, so let's say that large spin you take to be 20. Okay, and this large S is what helps me go to the classical limit later, but I'll come to that. And N is the number of excitations. So it doesn't seem to really be a simple function of N or S, because you see here we have already reached 100 and we don't see any thing of it going back. But presumably there is a recurrence, which is probably very, very far. But from what we have done, it really doesn't seem to be guided by some simple, not even some multiplicative factor. But now the question is, what is the steady state value of the imbalance? And it turns out, you can skip this, we don't have time. It turns out that the steady state value of imbalance actually has this collapsing form. If you multiply by square root of n by s, it's sort of there's some critical point here. Okay, so this is how we have to take large and largest limit. So even if you take large and largest limit, it is not a sharp this thing. So it seems that imbalance is 0 here, but then it smoothly goes to 1. Okay. So typically, when you take large system size limits, you expect things to get sharper and sharper. So this basically hints at the fact that there is a possibility of mixed phases here, which is neither random matrix theory nor Poisson. That comes to Abhijit's question that there's an example here where no matter what you do, what I scale, I don't seem to be getting either this or that. Of course, deep inside I'm completely in Poisson. I didn't tell you that it is Poisson, but here I'm completely in random matrix theory. Okay, so this is my this thing. So these are some deep numbers. 2 and 10 are basically, if you see that 2 is somewhere here, 10 is somewhere there, and there is no doubt that this is all Poisson here. 2 is random matrix theory and 10 is Poisson, because more it localizes, and this is Poisson, and this is the plot of average R versus lambda, and you see in the largest and larger limit it seems to converge to a profile. It doesn't become this. Okay, so the chances are that
there are no crossings, so it's unlikely to be a translation.
It's unlikely to be a translation, and in some sense it is not a it's not an extended system, although there is a large S concept. It's not like if you have like hundreds of these units and then I scale the number of units, then you should see something. But that's a very difficult, almost impossible to do problem. But under a dimer, this is what happens. So this is random matrix number 0.53, and this is all Hermitian. Okay, so Hermitian expectation one is 0.53, and it should go to 0.39. Okay, so these are the values that I to recall. Okay,
if you really go to the largest limit of the spins and put some sort of a Hurstine-Primakov type representation,
yes,
then you will get an almost. Is that a solvable thing where you can at least do up to 1 over S or something?
Yes, I'll show you. So if you do the Hurstine-Primakov and you can map it to a classical problem also, and it turns out the classical model itself is interesting also. It also has this localization, delocalization, transition, and this classical model itself seems to have some mixed phase space. And I have a slide on this Hurstine-Primakov. But okay, this is my chart. Zero imbalance, random matrix, ramp, finite imbalance, Poisson, and no ramp. This blue data is our so considering these rich properties in the quantum model, it will be interesting to study classical limit in itself, because then I can ask if I can study some of those conjectures of classical quantum correspondence and so on. So that is one thing, but the classical model in itself is very interesting, and it facilitates to think about classical quantum conjecture. So this is my last 2 slides, so it will end eventually. So this is what Rajdeep was saying. In these largest models, one thing is you can do this Hurstine-Primakov transformation, and basically here what you do is you take this S and you make this transformation. You introduce B bosons. Remember the other ones were A bosons. They are authentic ones. They are there. A bosons. You introduce B bosons, and you take this B bosons and make X and P variables out of B bosons, and then replace these operators with real numbers. You end up with a classical model. This is a classical, highly non-interacting classical network. So okay, then you can write equations of motion for classical model and so on. And this is a network, and n equal to 2 will correspond to timer. But then you can ask the same questions in classical model. I have 2 classical oscillators, not just 2 oscillators. Each unit has X and XC and XS. C was denoting cavity bosons, and S is the spin bosons. So the bosonized versions of the spins. And then you can ask the same question: what happens if I start with the initial condition and so on? And it turns out that you can also define imbalance. And it turns out that it is reasonably obvious, but not entirely obvious also, that it turns out that you have a complete delocalization when lambda is 2, and when lambda is 10, it is stuck. Okay, so this is so it's a classical model, and basically there are a lot of things about this classical model that we have got interested in, because it doesn't seem to be clearly chaotic or non-chaotic, and the imbalance itself seems to have a distribution. Various initial conditions. So if the imbalance goes to 0, you would expect that to be a statement independent of initial conditions. No matter what I start with, I should go to 0. If the imbalance gets stuck, then that should be about, if you start with the initial condition, it is likely to get stuck. So if I start with an ensemble of initial conditions corresponding to some fixed excitation sector of the quantum problem, but even here, just classically, if I start with some ensemble of initial conditions, I should check what is the distribution of my imbalance. And it turns out that even it's not very clear that it is like an ergodic system or not. So it's a nice model to study mixed phase space. What happens when the system is neither chaotic nor non-chaotic? This is still ongoing this thing. So this is a distribution of imbalances. You have all sorts of imbalance possible from -1 to 1, depending on your initial conditions. But when lambda is 2, depending on initial conditions, your imbalance just goes from like -0.04 to +0.04. It's still small, but it's not a delta function. Perfect case would be that you should just have one point at 0,0, right? Because that would be like 0 imbalance, and so it's an example to study mixed phase spaces, and Lyapunov exponents are also there's some interesting Lyapunov exponent distribution. Okay, so I'll end by saying that we studied some properties of Hermitian and non-Hermitian random matrices. We studied spacing statistics, spacing ratios, and spectral form factors. We discussed quantum Hamiltonians, both Hermitian and non-Hermitian, and spectral properties of open systems, and some localization, delocalization in large spin diamond models and some classical limits. So, so these are some outlook where we still want to understand classical quantum conjectures and other diagnostics such as out-of-time ordered correlators and distribution of Lyapunov exponents in these models, and understanding mixed phase space and classical quantum correspondence. You might have noticed that I was talking only about eigenvalues in this whole talk, but there's also eigenvectors, and what happens to eigenvectors, left-right eigenvectors of non-Hermitian random matrices and Hamiltonians. This is something which we have just started exploring. Thanks. Yeah.
Questions from the Zoom audience? Not any questions from the physical audience?
Yeah. In the study of black holes, the following matrix model has recently become popular, which is you study an integral over just ordinary unitary matrices. But the Lagrangian for the unitary matrices, instead of lambda trace u plus lambda star trace u, the Lagrangian becomes complex. Do you know what would happen to the saddle point equations of such models? So the unitary matrices are just ordinary unitary, but the Hamiltonian has become, the weighting factor has become complex.
Oh, weighting factor. But then this is some effective non-Hermitian.
Well, you're integrating only over your actual unitary matrices.
I see.
But the saddle points are presumably going to be off the real axis.
Right. The saddle point equation.
The saddle point equation will presumably take you off the integration contour.
Yes.
And so it may actually end up looking quite similar to what you were.
Oh, okay.
I was thinking, but
Right. I see. No, but what is the analog of the eigenvalues now? I mean, here you have a saddle point equation, and the saddle points are on the complex plane.
You have a saddle point equations for the eigenvalues. For the fundamental level, the eigenvalues are phasors because you've got a unitary matrix.
Right.
But the saddle point, often an integral over a particular contour and saddle points off that contour.
Oh, okay. Right.
And I think this is what's probably going on in those models.
Okay, right.
So it might be that you get the analog of your discs or something like that there. I was just wondering if you...
Right. Maybe, yeah.
Because the matrix measure is still written in terms of trace of them.
The matrix measure is the usual unitary R measure.
So you can decouple to the go to the eigenvalue measure.
You can go to eigenvalues.
And you will get random on.
You get random on, and you're going to be doing an integral over the individual eigenvalues. Okay. But now the weighting factor is complex. So you write down the 9 saddle point equations, you have no real solutions.
Right.
So it looks like the saddle points will be taking you off your contour.
Right.
And I was wondering whether you get something similar to the kind of thing you were.
Right, yeah.
And at the fundamental level, it's a unitary matrix model.
Right.
It's just that there are complex numbers in the action.
Right.
I was just wondering whether you encountered something like that.
Not encountered, but yeah, that's yeah.
So the semicircle law now it becomes a complex plane.
It becomes a disk. You're saying it will.
I was wondering, actually I don't even know, but I was wondering whether it remains an arc or spreads out into a 2-dimension.
Okay.
Your results sort of seem to suggest it might become 2-dimensional.
Right.
I don't know if that's clear.
So, most of the things, there are some things where we get an arc, but a small arc cloud. I don't know if that is relevant. Some of the Hamiltonians you don't.
You ever get exactly an arc, but off the somewhere in the complex plane. You're really 1-dimensional.
No, I mean that is very. No, because that doesn't happen.
So only for complex random matrix.
Unitary. So the matrices are unitary. Integrals over the R measure of unitary matrices.
Right.
Nothing funny in the integration. Just that what's upstairs is complex.
But your averaging is complex.
No, at least we don't because that is possible. That would have been possible. There's nothing forbidding that. Just an arc in the complex plane, but somehow it never happens. It's an almost arc. There's some very small spread, but you want a perfect arc, right?
I mean, I was hoping the larger limit would become a perfect arc.
No, it doesn't happen. No. Yeah.
You mentioned that what happens if you take a multi-symmetric Hamiltonian cross translation? If you take a non-Hermitian multi-symmetric,
Right.
do you see random matrix behavior or something different?
So I think there is some literature on that, but I think you should on one side you should probably see random matrix behavior, I think. And then probably
On the real side, you get
they'll again be collapsed to real, but there's some
statistics.
but I think not much is known. I think there also
The other question, you mentioned this Lindblad approximation. If I take an integral model and let's say a non-integral one, and I look at the subsystem and approximate with the Lindblad equation, will the Lindblad equation inherit the integrability section?
So there also is very little work. But suppose you have an integrable model, and then let's say you add Lindbladians in a specific way. There are examples where it somehow retains integrability. But typically, if you add Lindbladians, it will not remember the integrability.
But take a large system and approximate the subsystem with the Lindblad equation, then it won't integrability property of the bigger system.
No. So the thing is, if you have a large system and you just couple of them to.
But take a subsystem and approximate its dynamics with the Lindblad.
It doesn't matter what large system you have. Now have a small system with a Lindbladian dynamic. So he is saying that for a generic Lindbladian you will not.
So it will be a generic.
Yeah, because you see the point is, even if your system is large and you couple of them to Lindbladians, microscopically they are coming from some infinite paths here. So each Lindbladian itself coming from infinite. So effectively it will go to
You
the.
cannot see the integrability of the bigger system by looking at it.
So typically Lindbladians will heat you up to very high temperatures.
Exactly.
Much quantum mechanics.
Exactly. So in that also there are various ways to do Lindbladian and then what happens with non-Markovian? They're all very complicated questions. I mean, yes.
Any further questions?
One question, is there a sense in which one can define an entanglement spectrum now where you have these two timers and so on, and you couple it? Is there a sense once I go into these complex things of an entanglement spectrum which would now in principle be complex, or is there no such notion?
Okay, so first of all, the dimer thing I mentioned was just isolated system.
Okay.
But let's say that in general, so that also whether you can lift all the results of Hermitian problems and build. I'm not sure. So that I'm not sure if it's even done. That is.
But it is actually a physical evolution.
Which one?
And the eigenvalues of rho should just continue to be positive.
Yeah. So in the Lindblad setup, the rho is rho respects trace preserving.
Not just trace preserving. I mean, positive eigenvalues.
Yeah.
It's a positive number. Yeah. But in general, for its generic non-Hermitian, Hamiltonian, it's not.
Right.
Then the question is there some generalization? I don't know.
Yeah.
Also, it would be, the other way, it would be nice to analyze that particular kind of non-hermiticity, which is
positive maps.
Positive response.
Right.
Any further questions? Okay, if not, let's thank once again.